Good morning, children. This is lecture 6 of chapter Chemical Kinetics. In this lecture, we will study about catalysis. In the previous lecture, we studied molecularity of a reaction and some solved numericals based on Arrhenius equation. Now, in this lecture, we shall discuss catalysis as I told you. Catalyst and catalysis. The substance that alter the rate of a reaction but itself remain chemically unchanged at the end of the reaction is called catalyst. You all know about it. And the above process is called catalysis. So catalyst is the substance and catalysis is the process. Now the catalyst which increases the rate of a reaction is called positive catalyst, and the phenomenon is positive catalysis. The catalyst which decrease the rate of a reaction is called negative catalyst, and the phenomenon is known as negative catalysis. Now some examples of positive catalysis. Decomposition of KClO3 takes place rapidly at lower temperature when a small amount of MnO2 is added to it. So you all know about it. KClO3, when it is decomposing, it is giving you O2, but MnO2 should be present as catalyst. Decomposition of hydrogen peroxide takes place rapidly in the presence of colloidal sulfur. So the sulfur is acted as catalyst. Now oxidation of hydrochloric acid into chlorine is accelerated by the use of CuCl2. So these all are acting here as catalyst, and they are positive catalysts. They are increasing the rate of the reaction. So they are known as positive catalyst. Now basis of positive catalyst. Why they are called as positive catalyst? As you know that they are decreasing the rate of a reaction. Okay. Now what actually the positive catalyst is doing? They are lowering the activation barrier for the transformation. How? By introducing a new reaction pathway. That means this first graph is showing this is the activation barrier. Okay, the reactant has to be crossed, they has to cross this activation barrier. They has to be activated up to this much, and then only they will give you a new product. But the second graph is showing you with the green line, this is the graph is showing with a catalyst the reaction is going on. What the catalyst is doing, it is decreasing the activation barrier. Okay, it's a new pathway it is giving. This dotted line is the pathway for the previous one, that means without catalyst. And the green one is showing with the catalyst. And you can see that it is decreasing the activation barrier for the reaction. Examples of negative catalysis. Oxidation of sodium sulfite by air is retarded by the presence of alcohol. That means alcohol is acting here as a negative catalyst. Decomposition of hydrogen peroxide decreases in the presence of acetanilide. Oxidation of chloroform in the presence of air is retarded in the presence of alcohol. Tetraethyl lead, which is known as TEL, decreases the knocking of petrol and thus acts as a negative catalyst. That means tetraethyl lead is also acting as a negative catalyst. So these are the examples of negative catalyst. Classification of catalysis. There are two types of catalytic process: homogeneous and heterogeneous catalysis. Both the process have industrial importance. In the following slides, we will study about the homogeneous and heterogeneous catalysis. Now, homogeneous catalysis. When the reactants and the catalyst are in the same phase and the reaction system is homogeneous throughout, the catalysis is termed as homogeneous catalysis. That means if the reactants are in solid state, the catalyst also in the solid state. If the reactants are in liquid phases, then the catalyst also will be in the liquid phases. If it is so, then it is known as homogeneous catalysis. For example, oxidation of SO2 into SO3 by oxygen in presence of NO. Now, the SO2 is reacting with O2. Both are in the gaseous state, you can see here. And NO is acting here as a catalyst, which is also in the gaseous state. So, the reactants are also in the gaseous state as well as the catalyst is also in the gaseous state. So, it is an example of homogeneous catalysis, which is giving SO3. Now, hydrolysis of an ester in presence of mineral acids. Ester and water both are in the liquid phase. H2SO4 is a mineral acid acting as a catalyst, that is also in the liquid phase. So, it is an example of homogeneous catalysis. It is giving you acid and alcohol. Now, hydrolysis of cane sugar in presence of mineral acids. The same way, cane sugar solution, that means it is a liquid. H2O is a liquid phase and mineral acid also in the liquid phase. So, it is also an example of homogeneous catalysis, which is giving fructose and glucose. Now, transition metal compounds participate in homogeneous catalysis as they have the ability to change their oxidation state. Now, let us see the reaction. The reaction between iron 3 and vanadium 3, and this reaction is catalyzed by Cu2+. What is happening here? In the first step, this Cu2+ is reacting with one of the reactant, that is V3+, and it is giving Cu+. That means the oxidation state is changing from +2 to +1, and we are getting V4+. Now, in the second step, this Cu+ is reacting with another reactant, that is Fe3+, and it is giving Fe2+, and again this Cu+ is changing to Cu2+. Okay, so that means at the end we are getting Cu2+, which is acting as a catalyst, unreacted. So what is the overall reaction? Fe3+, V3+, and we are getting Fe2+, V4+, and Cu2+ will come out as it is. It is not taking part in the reaction. Heterogeneous catalysis. When the reactants and the catalyst are in the different phases, the catalysis is known as heterogeneous catalysis. Example, combination of N2 and H2. You can understand that both are in the gaseous phase. In the presence of finely divided iron, that is the Haber's process, we are using that. Now see, N2 and H2 both are in the gaseous phase and iron is in the solid phase. We are getting NH3 by Haber's process. Combination of SO2 and O2. Both the reactants are in the gaseous phase. In presence of platinum metal or vanadium pentoxide, that is a contact process. So SO2 is in the gaseous phase, O2 is in the gaseous phase, and platinum and V2O5 both are in the solid phase. We are getting SO3. Now oxidation of NH3 by O2, that means both are in the gaseous phase again, and this is happening in presence of platinum gauge, that is Oswald process. The platinum is in the solid phase. That means the reactants and the catalyst both are in the different phases. So that is known as heterogeneous catalysis. The example of heterogeneous catalysis is the hydrogenation of ethene to ethane using nickel as catalyst. The reaction is given here. First of all, ethene with a double bond, nickel is reacting with ethene and it is loosely bonded with ethene. Now after that, hydrogenation, when the hydrogen is reacting with that, then nickel is now attached loosely with one carbon atom, and then with the second hydrogenation, nickel is coming out. It is not taking part in the reaction, it is acting as a catalyst here, and we are getting ethane. That means here ethene and ethane both are in the gaseous state, and the nickel is acting as a catalyst which is in the solid state. So it is an example of heterogeneous catalysis. Characteristics of catalyst. The catalyst remain unchanged in mass and chemical composition. In the reaction, you all know about it. Catalyst is not taking part in the reaction, so it remains unchanged in mass and chemical composition. This is activity of catalyst. A small quantity of catalyst is required in a reaction. The catalyst does not change the equilibrium constant, but the equilibrium approaches earlier. With the help of a catalyst, the equilibrium approaches earlier, but it does not change the equilibrium constant. The catalyst is specific in nature. It means by the change of catalyst, the nature of the product is also changing. Or you can say that specific catalyst for a specific reaction. For example, CO, when it is reacting with H2 in presence of nickel catalyst, then we are getting C plus H2O. It will be, this O is not there. Okay, C plus H2O. Another, you can see that CO plus H2, when copper is acting as a catalyst, then we are getting HCHO. Again you see, when CO is reacting with H2, where ZNO and Cr2O3 is present, then we are getting CH3COOH. So you can see that the catalyst is very specific for a specific reaction. If you change that catalyst, the product is also changing accordingly. The catalyst cannot make impossible reaction to occur and does not initiate a reaction. Next is catalyst poison. This is a very important thing. There are certain substances which decrease or destroy the activity of the catalyst. Such substances are known as catalytic poison. For example, arsenic, if present, it can destroy the catalytic activity of platinum catalyst in the manufacture of sulfuric acid. Okay, so these are known as catalyst poison. Now, catalyst promoter. There are certain substances which increase the activity of the catalyst. It is just the opposite of the poison. Okay, it is increasing the activity of the catalyst. Such substances are known as catalyst promoters. For example, MO acts as a promoter in the manufacture of ammonia by Haber's process. You know the Haber's process, nitrogen and hydrogen reacting together in presence of Fe catalyst, it is producing NH3. Now if molybdenum is present there, it will act as a promoter which will enhance the activity of the catalyst. And the last point, the catalyst exhibits maximum activity at a particular temperature, which is known as optimum temperature. Okay, these are all the characteristics of a catalyst. Theory of catalysis. Number one, that is intermediate compound theory of catalysis. And the second one, adsorption theory of catalysis. Intermediate compound theory of catalysis. According to this theory, the catalyst react with one of the reactants first to give an intermediate. Now that intermediate will react with another reactant to yield the product, and the catalyst will come out as it is because the catalyst is not taking part in the chemical reaction. So how it is happening? What is happening? Suppose there is a reaction going on between A and B. Now first, the catalyst is reacting with A, one of the reactant, and it is giving you an intermediate. Now that intermediate is now reacting with B and it is giving you the product, and the catalyst will come out as it is. Just see this example. SO2 when reacting with O2 in presence of NO as catalyst, it is producing SO3. First of all, in the first step, what is happening? This catalyst NO is reacting with O2 and it is giving you NO2. Now this NO2 is reacting with another reactant, that is SO2, to give SO3, and NO is come out as catalyst. So this theory suggests that a catalyst provides an alternative path of lower activation energy by forming an intermediate compound with one of the reactants. This is known as intermediate compound theory of catalysis. Intermediate compound theory of catalysis is explained with the help of a graph which is shown here. Now it is saying that activation energy for the pathway with catalyst is less than the activation energy for the pathway without catalyst. Now in this graph you can see two lines. One is a black solid line and another is a dotted line. Now the black solid line is showing the pathway for the reaction without catalyst, and the dotted line is showing the pathway for the reaction with catalyst. Now from these two lines you can understand that the first line, that is the pathway for the reaction without catalyst, is having more activation energy. The reactant molecules has to be activated to a certain level, up to this much. They have to cross the reactant molecules, they have to cross this energy barrier to form the product. That means their activation energy is more. But as a catalyst is added to the reactants, that is AB is the reactant. If a catalyst is added to this, then AB and the catalyst, they are reacting together. First, one reactant is reacting with the catalyst to form an intermediate. That intermediate, to form that intermediate, the activation energy is less than the previous one. That is the activation energy without catalyst. Now it is forming a intermediate product, that is A catalyst, and B is not reacting at that time. And when they are forming that intermediate A catalyst, their activation energy is up to this much, from here to here, up to this much. So they have to cross this barrier. They have to cross this energy barrier, which is much less than the previous one. You can see this is the activation energy of the previous one. So they have to cross a much less energy than the previous one. And then after that, when they cross that energy barrier, and then they are reacting with B and giving the product AB, and the catalyst is coming out without taking part in the reaction. Am I clear to you? That means the work of the catalyst is to decrease the activation energy by forming an alternative path. So the reaction can then be speeded up by increasing the fraction of molecules that have energies in excess of the activation energy for a reaction. Now next is the adsorption theory of catalyst. Adsorption theory has been proposed to explain the mechanism of heterogeneous catalytic reaction, contact catalysis, particularly involving two gaseous substances over a solid surface. The heterogeneous catalysis, that is a gaseous reaction on a solid surface, may be explained by the theory how A gas, B gas, and the catalyst is in the solid phase, and we are getting C and D, both are also gas. So that means the reactants and the catalyst, they both of them are in the different phases, different states. So that is known as heterogeneous catalytic reaction. Following four steps are involved in the heterogeneous catalysis. The first is diffusion of reactants at the surface of the catalyst. Catalyst is a solid. Now the reactants are diffusing at the surface of the catalyst first. Then the adsorption of the reactants at the surface. So catalytic surface is adsorbing the reactants. Adsorbing means it is a surface phenomenon. The reactants are not going inside. It is whatever happening at the surface only. Then third is a reaction of the reactants at the surface. As I told you, the reaction is happening at the surface only. Surface of the catalyst. Then desorption of products from the surface. Then again the products are coming out from the surface, leaving behind the catalyst as it is, because the catalysts are not taking part in the chemical reaction. Look at the figure. The figure below demonstrates various steps in heterogeneous catalysis. See here, there are two reactants shown in green and yellow color. And this is the surface of the catalyst. Now in the first step, the green molecules are coming and sitting at the surface of the catalyst, or they are landing on the active sites of the catalyst. And the second step, the yellow molecules are also coming and sitting with the green molecules, maybe in a proper orientation, so that the more collisions can occur, and because of the collisions it will give the product. These are the product. So they are coming out from the surface of the catalyst and leaving the catalyst unreactive. They are not taking part in the chemical reaction. Now let us see what is written here. Step 1. Incoming species land on an active site and forms bond with the catalyst. It may use some of the bonding electrons in the molecules, thus weakening them and making a subsequent reaction easier. Step 2 and 3. Adsorbed gases may be held on the surface in just the right orientation for a reaction to occur. I have already told you. The adsorbed gases means these are the reactants. They may held on the surface of the catalyst in just the right orientation maybe, and that is why the reaction is taking place. This increases the chances of favorable collision taking place. There is a rearrangement of electrons and the products are then released from the active sites. I hope you have understood. Explanation of characteristics of heterogeneous contact catalysis based on adsorption theory. Various characteristics of contact catalysis may be explained with the help of adsorption theory are given as follows. Increase in reaction rate by using catalysis. The catalyst provides an alternative pathway by lowering the activation energy. You all know about it. This results more number of reactants passing through the energy barrier and hence the rate increases. That already I explained it to you. The catalyst is specific. The reactant molecules get attached to the surface of the catalyst. This is also called chemisoption. This is a new word, chemisoption, chemical adsorption. A catalyst has specific affinity towards a particular reactant, and that is why a catalyst is a particular catalyst is required for a particular reaction. Hence, a particular catalyst is suitable for a particular set of reactants. The catalyst remain unchanged. Desorption of the reaction products from the catalyst surface leaves the catalyst unchanged chemically and quantitatively. That already I explained. Catalyst is not taking part in the chemical reaction. So in the reaction, after the reaction, the products are forming. The catalyst remain unchanged. A small quantity of catalyst required. This also I told you. Adsorption and desorption processes being continuous and simultaneous in nature, there is always a vacancy in the surface sides for the reactant molecules. Hence, only a very small quantity of catalyst is needed. Finely divided catalyst works better. Finer the catalyst particle, greater is the surface area available for the reactants molecules. Therefore, finely divided catalysts work better. Promoters accelerate the reaction. How promoter is accelerating the reaction? A promoter changes the crystal lattice of the catalyst, which in turn increases the active sites available for reactant molecules and catalytic activity increases. I hope you have understood. The poison retard the reaction. This also you know. How poisons retard the reaction? Poisons get adsorbed into the catalyst surface preferentially and reduce the number of available active sites for the reactant molecules. Hence, the catalytic activity decreases. I hope it is clear to you. This is the end of chapter Chemical Kinetics. Please go through all the videos carefully.